I dug up some of my old physics notes from 20 years ago. Hey guys and gals, welcome to my channel again. On this channel, I try to see the world in terms of what I don't understand, focusing on the bigger questions. One big question is, can the future help shape the story we tell of the past? So similar to my previous physics video, today I will show you a simulation of another famous physics thought experiment. It's called the delayed choice quantum eraser experiment. For example, a distance of 10 light years. I first learned about these experiments in 2004 in Brian Greene's book, The Fabric of the Cosmos. Let me read to you what he said in that book. So Brian says this: "The results are truly stupendous. We must emphasize that the future measurements do not change anything at all about things that took place in your experiment today. The future measurements do not in any way change the data you collected today. But the future measurements do influence the kinds of details you can invoke when you subsequently describe what happened today. We thus see that the future helps shape the story you tell of the past. These experiments are a magnificent affront to our conventional notions of space and time. Something that takes place long after and far away from something else, nevertheless, is vital to our description of that something else. In other words, when we attempt to describe something that is happening today, things that happen in the distant future and far away can help us understand what is happening today." These are simulations of 5 quantum particle path experiments. These are real experiments that were done by physicists decades ago. So the first one is the beam splitter experiment, and then I'll go on and show you experiment 2, 3, 4, and 5. The fifth and final experiment is the delayed choice quantum eraser at a large scale, at an interstellar scale. So each of these experiments provides the building blocks for the next experiment. Here are the components of the beam splitter experiment. There's a laser that emits light, so it emits 1 photon at a time. Each photon is a quantum wave packet. So it's a low intensity laser where only 1 photon is emitted every few seconds. The next component is a beam splitter. 50% of the photons are reflected up. 50% of the photons are transmitted to the right. In the quantum realm, the photon takes both paths at once. In other words, the single photon is in a superposition of going left and right. Then there's a mirror that reflects the photon that went up. It reflects it towards this detector screen, which is a photographic plate. It records where each photon lands. It builds a pattern over many impacts of those photons. In the quantum realm, the photon takes both paths, so we will see interference fringes where the peaks and the troughs of the photon waves interfere with each other and cancel each other out. In the classical mode, we will not see those interference fringes. So I'm going to go ahead and start the experiment in quantum mode first, with time slowed down so that we can see it better. Right, there's the photon emitted. It hits the beam splitter, and now it's in a superposition of left and right. The laser continues to emit photons one at a time, and each of those emitted photons are in superpositions and they impact the detector screen. Now I'm going to speed up the quantum experiment so that we can see the result, the final result. You can see it's building up the interference fringes. All right, I'll go ahead and stop the experiment. So the interference is represented on the detector screen by bright and dark bands. As we can see here, this is a bright band, there's a dark band, here's a bright band, here's a dark band, and so on. There were 226 photon impacts in this test. Okay, I'm going to reset the simulation now and switch it to classical mode. This is the mode where we're used to seeing, where one photon takes one path through and there's no interference. So let me slow it down and start it. So you can see the photon, each photon emitted only takes one of the two paths. It doesn't take both at the same time. So this is happening because we're observing the photon. We know where the photon's going. We've already observed it. Whereas in the quantum mode that I showed you earlier, we weren't actually observing the photons along the path. But now we're seeing which direction they went. If I speed up time, we'll see there's no interference pattern. It's just the photon impacts kind of build up in the middle of the detector screen and they kind of spread out a little bit, but they're mostly packed up in the middle. All right, let me go ahead and pause it. This is the delayed choice experiment. Same experiment as before, but we've added a photon detector. It's a new device that tells which path the photon went. It's positioned after the beam splitter, so when the photon takes both paths at once, we'll be able to tell which path the photon actually took by observing it with these which path detectors. There's two of them. There's one on the upper path, and then there's one on the right path as well. When I start the experiment, the which path detectors will both be off. Run it. Photons are in a superposition. Speed it up. You can see the interference pattern building up. Now I'm going to switch the experiment. I'm going to turn on those which path detectors. And now we can see the interference pattern is being wiped out. This is the quantum eraser experiment. It's a different kind of experiment. There's some new components here. So there's a barrier with two slits. This is the upper slit here, and then this is the lower slit here. There's also photon tagger devices that allow the photon to pass through the slit, but they change the photon's spin orientation depending on which slit it passed through. So photons passing through the upper slit are tagged with spin up, and photons passing the lower slit are tagged with spin down. There's also a photon marker or photon tagger erasure device added to this experiment. It manipulates the photon's spin to point in one and only one direction. And we still have the detector screen but it also records the photon's spin orientation as well as recording a dot at the photon's impact location. So I'll run the experiment with the devices off. I'll speed it up. Since we're not observing any of these photons, the interference pattern builds up. Now I'm going to turn on the spin taggers. Now we know which of the two slits each photon's actually going through, and we lose the interference fringes. Now I'm going to turn on the spin eraser. And now we can see the interference patterns building up again by those light and dark bands. You can barely see them on this simulation. It's just an illustration. This is the delayed choice quantum eraser experiment at a small scale. It's based on the beam splitter experiment, but there's some new devices added to this experiment. There's something called a down converter. There's two of them. There's an upper down converter and a lower down converter. Each down converter takes one of the photons as an input, and it outputs a signal photon at 1/2 the energy, and that's directed along the original path towards the signal photon screen. And the second output is called an idler photon with 1/2 the energy, and it's sent in a different direction. It's sent down into this idler photon maze. Inside the idler photon maze, there's additional beam splitters: beam splitter A, beam splitter B, and beam splitter C. There's also 4 photon detectors that observe the photon: detector 1, detector 4, detector 2, and detector 3. So these are all only the idler photons come down into this maze. All of the signal photons end up going to the signal photon screen. Now on the signal photon detector screen, it's recording the impact positions of the photons, but it's also recording which of the 4 detectors they were observed at. Now inside of the idler photon maze, beam splitter A, it mixes the upper path idler photons, which will erase the which path information. Beam splitter B mixes the lower path idler photons, which erases the which path information. Beam splitter C is the final mixer. So all the photons here, they've lost their which path information. And those end up getting detected at idler detectors 2 and 3. Since both paths are mixed, the which path information is erased, so we get an interference pattern at detector 2 and detector 3. But at detector 1, those will have the upper path Euler photons only, and the which path information is preserved. In this subset of the photons, there's no interference pattern because we know which path they went through. Same thing with Euler detector 4. Now that one's for the lower path Euler photons only. Their which path information is preserved, so there's no interference pattern. So I'm going to run the experiment now. We can see some of the photons going down to the Euler photons are going down to the maze, and the signal photons are hitting the screen. Let's just speed it up. All right, I'm going to stop the experiment so we can look at the results. So for this experiment, we have to look at subsets of the points on the detector screen because the totality of the impact positions will not show an interference pattern. As we can see here, there's no interference pattern. They're all just kind of bunched up in the middle and spread out. Now if we look at detector 1, those are the photons that were detected at detector 1. There's no interference pattern. Same thing with detector 4, there's no interference pattern. But when we look at detector 2, we can see the interference pattern with the dark and light bands. Here's detector 2, and then here's detector 3. This is the same experiment that I just showed you, but at a large scale, like an interstellar scale. I like to call it the delayed choice quantum eraser experiment at a large scale. The only difference is we've moved the Euler photon maze to a far away location, 10 light years away. That's very far. It's the distance it takes light to travel in 10 years. All right, so let's start the experiment. I'm going to speed it up. All right, that's probably good enough. So I'm going to go ahead and pause the experiment, turn off the laser, and on the signal photon detector screen, the totality of the impact positions shows no sign of interference. But we have to wait 10 years for the Euler photons to arrive at the Euler photon maze at the faraway location. There, the 4 Euler photon detectors receive the Euler photons in sequence. So some of them go in detector 1, detector 4, detector 2, and detector 3. This is just an illustration. This experiment takes 20 years to run. Okay, so now the results, the Idler photon results, are being sent back to Earth, which takes another 10 years. The Idler data is being received. And once all the Idler data is received, the experiment is done. At least this configuration of the experiment is done, and we'll be able to look at the results. So if the Idler photons wound up in the detector 2, then highlighting the locations of the signal photon numbers on the screen shows an interference pattern. Detector 2. Yeah, so we can see the interference pattern, the dark and light bands. Same thing with detector 3. You can see those light and dark bands. If the Euler photons wound up in detector 1, then highlighting the locations of the signal photon numbers on the screen shows no interference pattern. You can see here they're just kind of bunched up in the middle. Same thing with detector 4. Okay, finally, this is the last experiment I'll run. It's the same experiment as before, but this time I'm going to alter the experiment after waiting 9 years. This experiment, again, it takes 20 years to run, but this time at about year 9, some people over at the faraway location, they're going to alter the experiment. That's what the delayed choice is. It's a choice being made far into the future at a faraway place. All right, let's run it. All right, that's probably good enough. I'm going to go ahead and pause it, turn off the laser, and now we're waiting 10 years for the Idler photons to travel to the distant location. So I'm going to resume the experiment. The signal photons have already been collected on the signal photon detector screen. The Idler photons, about year 9. I'm going to pause the experiment right now. And these people over here, far, far away, are going to alter the experiment. They're going to switch it to configuration number 2, where they've just removed the beam splitters there in the Idler photon maze, so it's not a maze anymore. So now only Idler photon detectors 1 and 4 receive the Idler photons. All right, resuming the experiment. Those Idler photons are being detected far, far away in the far future. Now we have to wait 10 years for the data from the Idler photon detectors to be sent back to Earth. speed it up a little bit. All right, the idler data is being received back on Earth. And once all the idler data results are received, we'll be able to look at the results. So highlighting the locations of all the signal photons on the screen shows no interference pattern. If we look at the subsets from detector 1, there's no interference pattern. Look at the subsets from detector 4, no interference pattern. And then detector 2 and detector 3 were removed